Yes, I'm ready.
Okay, Derek, would you like to redo your recording?
Recording has started, thank you.
Okay. Before we start, Derek has asked me to remind everybody if they could please mute their microphones and make sure your videos are off. I'd like to introduce Dr. Vanessa MacBride, who's going to give us a talk this evening entitled Black Holes, Fact or Fiction, which sounds very intriguing. Vanessa is an astronomer at the Office of Astronomy for Development and is involved in bridging the gap between astronomy and the community. She has a PhD in astrophysics, which she obtained at the University of Southampton. Her research focus is on optical and X-ray observations of binary stars, in which one of the stars is a neutron star. In addition to the occupation I've just identified, she's also head of research at the South African at the SAAO and an adjunct associate professor at the University of Cape Town. Most members who've been members for a while may remember that Vanessa gave us a fascinating talk on fast radio bursts a few years ago at the Molokren Hall in Eastcliff. So we're very pleased to welcome you back, Vanessa, and thank you very much for giving us the talk. We're looking forward to it.
Thanks very much, Jenny, and thank you everyone for having me again. It was great fun last time, and now that Jenny's reminded me what the talk was about, I remember it quite clearly. So a lot's happened in fast radio bursts since then, but today I'll talk a bit about black holes, which I find particularly fascinating. So let me just sort out the screen sharing quickly. Is everyone getting this this image?
Yeah.
Great. Okay, so as Jenny said, some of the work that I do is on X-ray binaries, and mostly I work on binaries that have neutron star companions in them. But quite a few of these binaries we think also have black hole companions. So let me talk a bit about these. And I think black holes are fascinating because they seem to open up like the possibility for you really to, explore in your imagination what could be possible in terms of science and science fiction. Sometimes you feel like the ideas suggested by some of these movies, are used to explore concepts like wormholes, time travel. Sometimes they're just used for pure terror. But, how much of these ideas are actually based, in what we think is likely and how much is just crazy. So let me tell you a bit about black holes, and then I'll go on to tell you a bit about how we learn things about black holes and the different kinds of measurements that we can make about them. So there's a few definitions of black holes. I've got two up here that I like. One of these is a nice quote that's black holes are where God divided by zero. And the other, probably a more prosaic kind of explanation, is a region of space from which nothing, not even light, can escape. And so both of these are right sort of in their own ways. But in a way, the concept of a black hole is not that new. This is a quote by Reverend John Michell, which was published in 1784. So, well over 200 years ago in the Philosophical Transactions of the Royal Society. And so in this quote, the Reverend Michell explores if the semi-diameter, so the radius of a sphere of the same density as the sun, were to exceed that of the sun in the proportion of 500 to 1, then a body falling from an infinite height towards it would have acquired at its surface a greater velocity than that of light, and consequently, supposing light to be attracted by the same force in proportion to its vis inertia with other bodies, all light emitted from such a body would be made to return to it by its own proper gravity. So I find this really interesting because there are some concepts in here that we know now are not correct, but actually there's a surprising amount of intuition, that turns out to be correct. I mean, for a start, we know that, it's not quite the same force for light as it is for matter, but yet we still have this concept that's highlighted in blue, that all light emitted by such a body actually cannot escape and is made to return, in some sense, by gravity. So when we think of gravity, we think about it very much, well, at least I do, in terms of, Newton's law of gravity. So a simple equation where the force of gravity is proportional to the mass of the two objects undergoing the attraction and inversely proportional to the distance between them. And so we think about this very much as, the act of like an apple falling from a tree, or that kind of thinking. And for most of our lives and general life on Earth, this is a perfectly adequate description of gravity. But in the earlier 20th century, gravity got a bit of a makeover by this guy, Albert Einstein. And he really explored thinking about gravity in a very different sense. Not so much in the sense of a force between two objects, some kind of this invisible attraction, as gravity were, explained by Newton. But Einstein thought about this in terms of a sort of a warping of the fabric of space-time. And so he explained this in a set of 10 differential equations, and that representation is given by this equation here, G mu nu equals some kappa T mu nu. And really what this is telling you is that on one side of the equation is representing matter, and the other side of the equation is representing something called the curvature of space-time. And very simply, putting matter in space curves space. And so the analogy that I use to think about it, because it's kind of hard to think of a 3D thing being curved, is in 2 dimensions, if you put a sort of a rubber sheet or an elastic sheet down, and then you put a pool table ball or a billiard ball or something in it, and it sort of causes that sheet to distort slightly. That is kind of the effect that you then can think about in 2 dimensions and then extrapolate up to 3 dimensions. And so the idea is that if you put a ball of matter in space-time, as is shown in this image, this space-time then becomes curved. But gravity is then just objects moving along the shortest path in curved space-time. So if your space-time was totally flat, if your rubber sheet was not stretched, then the shortest path between 2 points is just a straight line. But when that sheet becomes curved, then sometimes the shortest path between 2 points on that curved space-time is actually a curve. And so it's this sort of path minimization problem that we see then as gravity. And so this was a very different way of thinking about things. And not many years later, somebody came up with a solution to these 10 field equations, the gravitational field equations that I showed in the previous slide. And this is a picture of Carl Schwarzschild here. And he solved these equations for a simple case where you had a spherically symmetric, so like a sphere that was not at all rotating in space-time. And so he ended up finding a couple of interesting things. One is that the curvature of space-time seems to go sort of down to infinity at the center of this spherical object for particular ratios of mass over radius. And so you end up with this thing called a singularity, this divide by zero problem. The other thing that he found was that there's this particular radius here, this is it, the Schwarzschild radius it's called, which is just given by 2g is the gravitational constant, m is the mass of this ball that he's thinking about, and c here is the speed of light. And so this is the definition of the Schwarzschild of a black hole in terms of this solution. An object smaller than its Schwarzschild radius is a black hole. So you can really make a black hole in this context out of anything. You can make a black hole out of the sun if you shrink the sun down so that all of the mass fits inside its Schwarzschild radius. In that case, the Schwarzschild radius of the sun is 3 kilometers. So you have to fit all of that mass down into within 3 kilometers. And that way you'll make a black hole out of the sun. If you wanted to do the same for the Earth, you've got to shrink it down really tiny to a centimeter, right? To within a centimeter. And once you've got that kind of mass to radius relationship, you end up with this black hole, and you also end up with a singularity, this kind of divide by zero problem in the middle. And this puzzled mathematicians and scientists for quite some time, whether this singularity was just sort of a problem of the description of the maths, i.e. could you change coordinate systems and get rid of it, or was it actually a physical, divide by zero problem? I'm not entirely sure, to be honest, if that is solved. I think it's been left. So that's kind of, the formal definition of a black hole. But what do we really know about black holes today? And so looking at these, I'll first look at the weight of these objects. We've got, or rather the mass. We have black holes that are huge, so up to 1 million or more solar masses. These are sort of galaxy-sized black holes. We then have what we call small black holes that we've seen evidence for. So these are kind of solar mass or a few solar mass black holes. We have almost no medium mass black holes. So not much between 10 solar masses and 1 million solar masses. So obviously one of the outstanding questions is like, how do you get to 1 million solar mass black hole if you don't see, black holes merging and building themselves up to bigger masses? The other thing that we know about black holes today is that we know that black holes that merge and spiral in, very nearby ones, make these gravitational waves. And that was another of the predictions of Einstein's theory of gravitation, was that you should, as you see these very massive and small objects moving in space-time, they should be creating these ripples, and those will propagate outwards as gravitational radiation. And we know, we actually have only known for the last 5 or 6 years that we can detect that radiation. And then the final thing, the point that I wanted to say, that we also know that most black holes, both the huge ones that are galaxy sizes like this one, and the small stellar mass ones, seem to launch jets. So if you look over here, these are actually images of galaxies. That's the massive galaxy, and at the center of that massive galaxy is a black hole. And so you can see all these surrounding galaxies. This is an optical image. And then you can see the radio image here in the red, and you can see these very collimated, really narrow jets that seem to end up in this like messy lobes at the edges here. And this seems to be a process that happens somehow related to black holes, but also to neutron stars. And we're still trying to figure out exactly how those jets get launched. So in this picture, I'm showing a black hole. Can you see it?
Yes.
It's black. Great. I'm very glad that you can see it. So this is really one of the enduring questions, right, of black holes. Black holes are black. Space is black. How do you detect a black hole in space? And so we've got to go to the to how we learn things about the universe. And we've got a number of messengers, right? Most of us know light because we detect it with our eyes. But we can also measure things about space through particles. So they may be protons that are coming from the sun. There may be cosmic rays that are coming from greater distances. And now, just for the last couple of years, we know that we can also measure things in space through this gravitational radiations, these gravity waves that can come to us when we have masses that are interacting like this. And so we have loads of flavors of light. You of course know many of them already. We're most used to the visible part of the spectrum, which we can see with our own eyes. But of course, at the very high energy end, we also have X-rays and gamma rays. So here we have wavelengths that are close to the size of an atom. And then on the very low frequency side, we've got radio waves, which are kind of, the size of a hand or, a couple of centimeters in wavelength. And of course, the whole spectrum in between. And so I'm introducing this because some of our detections of black holes have relied on radio emission. Some have relied on optical emission in the visible part of the spectrum, and others have relied on X-ray and gamma radiations. And it's kind of by putting all of these things together that we can build up the circumstantial evidence of black holes. So this is supposed to be a rather violent looking picture of how a massive star evolves. And so we think that the small black holes that are just a few solar masses grow from the cores of big stars. So stars much bigger than our sun, stars that are about 15 or 20 times the mass of the sun. And they start off, the normal way, fusing hydrogen into helium, and slowly their cores become enriched with heavy elements. So they build up things like carbon in the core, and then in ever deeper layers, heavier and heavier elements, until eventually you end up with iron in the core. And at that point, you can no longer get energy out by fusion. And so the core, this whole star reaches a rather violent end because of the gravity compressing on its core. And so if the core is above a certain mass, you end up with this supernova explosion, and the core can collapse down either straight into a black hole, or sometimes it can go through a neutron star first and then into a black hole. And so these pictures here are supposed to be depicting what's left of the core as a rotating black hole. And this is obviously this collimated outflow that's shown as an artist's impression. And the outer layers of the star, there's a kind of a bounce here, at least for a neutron star, the outer layers just get blown off. And sometimes you end up with this sort of disk of material left that actually falls onto the black hole and sometimes creates radiation. So I think I went into a lot of detail there, but the main point that I just wanted to say is that most likely stellar mass black holes are formed through the evolution of stars that are much more massive than our sun. So I also wanted to just talk about how we make images. I mean, most of us are actually fairly well aware of how we create an image. I mean, we create images with our eyes all the time. And here we use lenses that focus light onto our retina as a detector, right? And it's the same principle with telescopes. Sometimes it's lenses, sometimes it's mirrors. But making images out of X-rays turns out to be quite a bit harder. For a start, you have to get above the atmosphere. So the atmosphere protects us against harmful radiation from the sun and from space. So it stops X-rays. And in order to study these objects, we've got to launch satellites like this Chandra X-ray Observatory into space. But the other problem with X-rays is that when you try to bounce them off mirrors, they just go straight through, which is not very convenient for astronomers. So you have to make a very interesting kind of mirror, which relies on the fact that if you just send an X-ray sort of at a very low angle to the mirror, at a very grazing incidence angle, you can just get it to bounce off. So instead of sort of making your mirrors point at the direction that you want to observe, you put your mirror the other way around, and you put loads of the mirrors like that. You nest them one inside the other, and then light comes in from the object you want to observe, grazes off these mirrors, and focuses some distance down. And that's what you can see in the picture along the bottom here. It's showing the mirror unit of an X-ray telescope, and you can see these sort of concentric gold rings here, which are, you know, a couple of hundred little gold mirrors, one nested inside the other. And that is a focusing X-ray mirror unit. So the focus and the resolution is nowhere near as good as we can get in the optical, because, you know, these X-rays are a bit hard to control, but we can use them to image some of these objects that we see in the sky. And this shows a zoomed in X-ray image of one of these black hole candidates, Cygnus X-1. So this is an object that was discovered in the X-rays in 1964. And this was shortly after, well, about 20 years or so after the end of the Second World War, and when it became possible really to use rocket technology to put detectors, you know, above the atmosphere. And it turned out that on the first couple of rocket flights, of course, the sun was detected as a very bright X-ray source. Scorpius X-1 was detected. And then as more missions explored the X-ray sky, we noticed quite a few X-ray objects along the galactic plane and out of it. And then a couple of years later, after Cygnus X-1 was discovered in the X-rays, it was localized, the X-rays were localized to a supergiant star. You can see it's in the constellation of Cygnus, the swan here. That's showing the position. And it's orbiting something unseen but heavy. So how do we know these things? There's some key important things that we need to know now to kind of get to the point of, well, you've seen something in the X-ray and something in the optical. How do you know that it's a black hole? And one of the things is a constraint on how big the X-ray emitting region of Cygnus X-1 can be. So you can place a limit on this from the time scale of variability of the X-rays. So the X-rays are quite variable, and knowing the sort of shortest time scale of variability can give you an idea of the size. So if you imagine the region of Cygnus X-1, this object, you know, maybe it's the disk of material around a black hole or whatever that's emitting the X-rays. One X-ray comes from this side of the disk of material towards you. Another X-ray may bounce off somewhere else and come towards you that way. And so the light travel time for this X-ray, you know, has got to be delta t, so that time is twice the radius, just this diameter here, divided by the speed of light. And so that is the smallest variation that you see in the X-rays, because anything smaller than that is pretty much wiped out, right, by the fact that the light travel time is much shorter. So using this constraint, it means that the diameter of whatever is making the X-rays in Cygnus X-1 is restricted to something like 100,000 kilometers. So that's not particularly big by astronomical standards. The other interesting piece of information that helps us to solve the puzzle is that when we look at the light from the optical star, that's the companion to Cygnus X-1, the X-ray source, we see that it is orbiting something, and it's orbiting something fairly heavy. And we know this through optical spectroscopy. Most of you are familiar with the concept of splitting light through a prism into its different colors. And if you made a plot here of the intensity at each particular wavelength, you might have something like this. And then, of course, you can take a whole series of these spectra at different times. And sometimes you can see the particular signatures in the spectrum moving slightly with respect to each other. Sometimes you see these spectra moving slightly to the red and then back to the blue. And that's as a result of the Doppler effect when you have this massive star orbiting something. So you can think about this using the same analogy that we use for the Doppler shift with sound, right? So if you think about a motorbike coming towards you, you hear a different frequency sound than you do if the motorbike is moving away from you because of the different spacing in the wavefronts. And so this exactly the same thing happens here with light in this image on the right. So I'm showing the spectrum of a particular star, and you can see these signature lines in the spectrum. If it's not moving, those lines should be here. But when the object is moving away from you, then you end up seeing those lines shifted with respect to their rest wavelength. And similarly, when the object is moving towards you, you see the lines shifted to the blue with respect to their rest frame wavelengths. And so this little simulation at the bottom shows what you can observe if you have two stars, each with their own lines moving relative to each other. So for the simulation, you are looking here from the green point, and this big blue star is star A, and then the smaller red star here is star B. And as they rotate about their common center of mass, you see that those lines shift across each other like that. And so that's actually what was observed for Cygnus X-1. If you looked in the optical, you ended up seeing actually only one pair of lines, but moving from the red to the blue in this periodic fashion. Don't freak out, because you don't need to understand these equations. The only thing I wanted to say is that, sorry, I've left a word out. It should be Newton's form of Kepler's third law. So Kepler's third law is a way that we use Newton mechanics to describe some of the orbits of two stars around each other. And basically, starting from that Newton's form of Kepler's third law, we end up with what looks fairly complicated, this thing f of m, which is just a mass function. And this just depends on two simple observable quantities. So 4 is a constant, pi is a constant, g is a gravitational constant, but p is the period of the change of the wavelength. So it's the orbital period that we can measure by observing the spectrum over time and seeing how those lines shift to the red and to the blue. The other quantity that we can measure is the actual shift in wavelength, which is a velocity, and that gives us this a sine I. And so what this mass function does is it gives us a lower limit on the mass of whatever the optical counterpart of Cygnus X-1 is orbiting. So that means we have two pieces of information. We know that the big bright star is not giving rise to the time variable optical stuff. That stuff is happening somewhere else. And if Cygnus 1 is orbiting another star, we also know that it's a fairly massive star. It's massive enough that you would be able to see the light from it if it were really a normal star like the sun. But yet you don't see anything. So we know that the Cygnus X-1, the massive star, is orbiting something else massive, but it's dark, and we know it's small. It's only 100,000 kilometers at most, which is the region that the X-rays are coming from. And so you end up with these limits. This is showing you here a table of limits in mass on neutron stars, which is the bottom panel, and then above the dotted lines are the things that we think are black holes. So you can see that there's some big error bars or big ranges, mostly because we don't know things like what's the inclination of the orbit, how's it tilted relative to us. And sometimes we don't have good constraints on the mass of the massive star that we're observing these shifts in. But what we think that we're seeing here is we're seeing light from this massive star, in the picture, this companion to Cygnus X-1 HDE 226868, and we're seeing that orbit around a black hole. Material from that star is actually being channeled into a disk around the black hole, and it's that disk of material that's giving rise to the very bright X-ray emission and the fluctuations in that emission. As that material falls into the gravitational well caused by this black hole that's bending space-time, that energy gets changed into heat and into radiation in X-rays. And so we think this is the picture that's building up for these objects. So there's some circumstantial evidence black holes. But let's have a look at other messengers, right? In particular, how to make a gravitational wave. So I think I forgot to share the screen with sound, but never mind, I think you'll be able to see the frequency quite well. So these two detectors, one based in the US and one based in Italy, the LIGO and the Virgo detectors, that have been particularly looking for the signature of the in-spiral of black holes that you would see as gravitational radiation. And a couple of years ago, they detected the first one. And you can see that what you end up seeing here is some sort of chirp signal. So a fluctuation that goes fairly quickly and then becomes much faster at the time of in-spiral. At the same time, the frequency changes. So it goes up from low frequency to a high frequency. And this is the typical chirp model for this kind of in-spiral that was, that comes directly out of Einstein's equations of relativity. And these things are really fantastic feats of engineering, I think. This is a kind of aerial view of one of these detectors. They have arms here that extend 4 kilometers orthogonally to each other. And they work by a method in interferometry. So you start at this box at the bottom of the schematic diagram here, shining a laser into a beam splitter. So it then sends the laser in one direction and in the other direction simultaneously. And so ideally, if nothing changes, the laser should reflect off the mirrors at the end of the arms and come back, and there should be no change in the detection when those two split lasers are detected. But if a gravitational wave happens to come along and distorts space-time slightly in one direction, which means it just makes one arm fractionally longer than another arm for a while, then you will end up with a slight delay in the signals that are coming back, those laser beams that are coming back along both arms. And those are the signals that have been detected in those chirp images I showed you later, where you see that sort of perturbation going faster and faster with the frequency changing. And it's just amazing that these things work at all, because they need to detect changes in length about 1,000 times smaller than a proton, which they do by incredibly sensitive time measurements of when those laser beams hit the detector again. It's really just, I'm amazed at the engineering that, these things can actually work. So we now have sort of two ways of detecting black holes. they're both stellar mass black holes. Actually, the in spirals that we've seen have been from black holes that had around 20 or so solar masses. And the circumstantial evidence for the double star systems, where one of the stars is a black hole, is also for stellar mass black holes. So let me go back to light and talk about what you would see if you were near a black hole. And this is kind of crazy, because even the perspective, your perspective becomes relative when you approach a black hole. So on the image on the left here, I just don't seem to be able to point at anything anymore, but the little black dot with all the rays sort of emanating or radiating from it, that little black dot is you. And the black lines are light from all around you that is coming towards you. And this big circle just off to the left, which is surrounded by a dotted line circle, that is the black hole. That's the event horizon. Remember, this is the same concept as the Schwarzschild radius. So if the whole mass of the black hole falls within its Schwarzschild radius or event horizon, that's when it's called a black hole. And the interesting thing about this is that light that is coming to you from directions, far away from the black hole acts as light normally would, and it comes in a straight line. But because the black hole distorts the space-time, you can see those red rays, some of the light actually appears bent by the black hole, and it almost comes to you from the opposite direction that it originated. And so that's what you're seeing in the graphic on the right, where you see the galaxy, Milky Way, almost reflected around the black hole. So as you're looking at the black hole, you see the galaxy as well, almost mirrored around the black hole. And these images, these three images along the bottom, are showing you what happens to the light rays as you get closer to a black hole. So the first one on the left is showing you sort of three rays, one from nearby a black hole, one from what's called the photon sphere, and one from just outside the event horizon. You again are the black point in all those images. The one in the middle panel at the bottom is showing you what you would see if you were located on that dashed line. That dashed line is called the photon sphere. And that's because any photon that you release tangential to that sphere will just continue to orbit that black hole forever. So it's actually a great way of seeing the back of your own head forever. And then finally, the image on the right-hand side is showing you that even very close to the event horizon there, right, you can see almost all of the light bent around the black hole and coming to you almost from behind. So remember, the event horizon is also that part, that light cannot actually escape out of. So you don't get any light, of course, coming to you from inside the black hole. So this is quite a cool simulation done by Uti Kraus a couple of years ago. And it shows your forward, side, and back cameras as you're approaching a black hole. And so you have to assume that each camera gives you a kind of a 90-degree view, 90 degrees forward, 90 degrees to the side, 90 degrees behind you. And you can see the black hole there in the forward image already with the galaxy reflected around it. So as we go down, we're now 100 event horizons away. As we go down to 20, you can see the black hole growing. And we're four event horizons away, 2.5. You can see the black hole already takes up your whole field of view in the forward camera, even though you're still 2 Schwarzschild radii away from it. And then as you extend much closer, because of that light bending effect, all the light from the rest of your field of view, even in your side field of view, is taken up by the black hole, and all that light is just coming to you from behind. So as you approach the black hole, you can see the whole universe is sort of the light from your whole field of view is just bent and coming, at you right from behind. So even though you have not yet crossed the event horizon, you're just outside of it. Everywhere you look looks like black hole. So really fascinating, fascinating stuff. And finally, to end this talk, I just wanted to show, I don't think you can give a talk on a black hole without showing this funny donut-shaped image that everybody went wild about 2 years ago. This is an image that's taken in radio waves. So we're looking at light again, of a black hole in a nearby galaxy, M87. And this was taken with the Event Horizon telescope. And so what you're seeing in this image is actually probably the radiation from the gas around the black hole, but you're then seeing the silhouette of the black hole itself on the background of that radiation. And that's what that is giving that sort of donut appearance. So the idea is really that this is now not a stellar mass black hole, right? This galaxy in M87 is one of these supermassive black holes. So we're looking at 1 million solar masses, not just 10 or 20 here. And the idea is that probably you're looking at this very central region where you have bright X-rays and also bright emission in the radio. And so depending on exactly the conditions of whether the black hole is rotating or how the matter is distributed, you can end up, with a whole variety of possible ways that emission, the radio emission, could look. And 3 of those options are shown on the right-hand side there. So those are models, and actually then this is the real image here. Obviously it looks it doesn't really look like either of those, but it's just for illustration purposes. And again, I think that like the engineering that's had to go in to create this image is just fantastic, because it relies on a technique known as interferometry, which is essentially using multiple telescopes as one. So in this little simulation, what you've got is 2 radio telescopes. And if you just use them as one telescope, effectively you end up with the longer baseline, which is the distance between them. And in optics, the resolution that you get, so how clear your picture is, depends on the size of your telescope or the baseline. And so as you move your telescope further and further apart, you can get a much clearer image. So that's, of course, why in optical we want to build bigger and bigger telescopes, not only because it gives us more light, but also because it gives us improved resolution. So with an interferometer, you have to make sure that you combine the signals arriving at the 2 or 3, or in the case of Meerkat in the Karoo, 64 dishes, exactly in phase, and then you can get these images of absolute superb quality. And this is feasible in the radio because the wavelengths are long, so you can keep coherence over a wavelength. It is possible in the optical, but it's a lot harder. And the Event Horizon telescope looks at taking this interferometry to kind of the next level. Basically, the idea here is that instead of just moving your telescopes 1 kilometer apart, or in the case of Meerkat, 8 kilometers apart, the Event Horizon telescope looks at moving these telescopes like half a world apart, so that you have thousands of kilometers between telescopes. And that allows you to get really amazing resolution on the sky. So the image of the black hole that I showed had a resolution of about 20 microarc seconds. if you think about that, and you look at the moon on the sky, the moon takes up about half a degree on the sky. That's 30 arc minutes. Then each of those 30 arc minutes is made of 60 arc seconds. And each of those 60 arc seconds is made of 1,000,000 micro arc seconds. And so the resolution of 20 micro arc seconds is just incredible. So that's the kind of resolution you need to image the shadow of that black hole on that sort of bright background radio emission from the galaxy, from M87. You may also have noticed that the M87 project and the Event Horizon project is far from over. They just last month released this new image, which shows roughly the same structure. But now you can clearly see these lines, which are supposed to show the direction of the magnetic field in this hot gas around the black hole. So it really is consistent with the idea of a rotating black hole. And I think I'm happy to end here and leave some time for questions if you have any. Thank you.
Hi, Vanessa. Hello.
Hi.
I just want to ask, I don't know, it was explained by somebody, but the reason why it's brighter on one side, I don't know if that's a complex explanation.
I think it's a complex explanation that I don't understand entirely myself. I think it's got something to do with the way that we're looking down on the black hole through the material that's around it. But in general, they've made a whole bunch of models. So the idea is that they've made a whole bunch of models that take into account things like the mass of the black hole, whether the black hole itself is rotating, and then the angle which we're looking down at the black hole relative to the material around it. And I think, I can't remember exactly which model it is, but it's a combination of those parameters that best fits the image that you see here.
Can I ask a question? Vanessa, I think your talk was just superb. You've simplified all these very difficult concepts. But just this last image now, we have a black hole in the center, which you say is rotating. But the way I look at that is like water going down a drain. So the black hole is stationary and the water's going around it, not the other way around. Can you explain that to me, please?
Yeah, you're right. So it does look like that, but I think there's no reason why the black hole is also not rotating. I mean, maybe you can think about it not so much as the black hole being the drain, but maybe that black hole being the vortex of the rotation, right? So I don't know if that helps with an explanation. Yeah, I've got to say these things like, I feel like I'm sometimes bending my mind to understand it myself. Okay. Did I miss something? Sorry.
Just a thank you.
Oh, okay. No problem.
I think that there's a sort of a frame dragging effect actually, so that the rotation of the black hole actually affects this it sort of twists space around it itself actually, which also has an influence on that. Yes,
that is right. So it really twists the space-time, exactly as you've said there. I don't know who was talking, but and you can see that as well in the magnetic field lines. Derek, yeah.
In that Cygnus X-1, what is the distance between it and its companion? Do you know?
No, not off the top of my head. But in order to get this type of accretion, sort of where you've got it's a kind of you almost squeeze the massive star into a teardrop shape. They have to be very close, you know, within a few radii of the massive star. So it's not like 50 or 100 massive star radii where it really is a few radii of the massive star. So it's fairly close.
All right. Thanks.
Okay.
Mind-boggling stuff.
Vanessa, if I may just ask a question here. Yeah, this business of the rotating black hole has always puzzled me as well. And Phil brought this up. I was about to, but he brought it up. And I'm very, I've always understood that the description of a black hole is that volume within the Schwarzschild radius. Now, how that can rotate, I can't quite picture. The surrounding area, all the gaseous stuff and so on, yes, understood fully, that's going to rotate at a very high speed. But within the Schwarzschild radius, I can't see how anything can rotate because you're going down to a singularity. Is that correct?
Yeah, you are going down to a singularity. And I agree, at the singularity, probably anything like rotation is undefined. But there is still distance between the event horizon and the singularity. So, I mean, I don't know that that's a good enough explanation. My thinking about it from an evolutionary point of view, or like a stellar evolution point of view, is that if you have the core of a massive star, it's rotating anyway, right? And so what stops the rotation at a collapse, you know? So I know that's not an answer to the question, but I think in a way it's natural for me that a black hole should rotate. But I agree that there's no such thing as rotation at the singularity. But I think there is still, you know, the Schwarzschild radius is not where the singularity is. The singularity is actually at the very point center of the mass.
Yeah, thanks, Vanessa. As Phil said, what a fantastic presentation you've given here. Most excellent. Thank you so much.
Okay. Thank you.
Anybody else got questions for Vanessa?
Vanessa, it's Vic Finn here. I haven't been able to get an answer. I think it was something I saw in relation to the Nobel Prize winners, the treble award that was given this last year, where I thought I heard that it was so intense a black hole that not even time could escape from it. And it showed it diagrammatically how, in fact, time at a slightly different pace was also drawn back and almost assumed, therefore, that it's infinity. I suppose that's your God divided by zero. But and then trying to look for it when I was questioned about what the source was, I heard a speech one of the three winners gave where they asked him what would he really hope to see coming out of science in his lifetime still, and he said a new quantum theory. Can you comment on either of those complications?
Yeah. So you're right. I mean, I've showed you, you know, some of the perspective effects that you can have around black holes, but there's also like really weird time effects, you know, in a way, as you fall across the event horizon, you would basically just, or it would look to an outside observer as if you were falling across the event horizon forever. So because of these kinds of, it's because in general relativity, time is just another dimension of space. So it's sort of treated with the same way, right? So, and we can go into some of those equations. I mean, they're just really, really strange. And then I think, yeah, it is very interesting because your second question, I think, relates to a quantum understanding of gravity, right? And so we've got this model for particle physics that is called the Standard Model, and it's based on this sort of idea that energies are quantized and that, you know, you can't have two particles with exactly the same properties in exactly the same state at any one time, at least for fermions. And so that theory, the Standard Model particle physics, brings together very nicely the three other forces of nature, right? Which is electromagnetism, the weak force, and the nuclear strong force. And they arrange very nicely in this model. But then you have gravity that doesn't seem to have an explanation that fits in with those other three forces. So I think it will be, I've got no idea how you could have a quantum understanding of gravity or where it will come from, or if we are waiting for yet another Einstein who sees the universe, you know, in a slightly different way and will be able to bring these concepts together in a way that we haven't yet thought of.
Thank you.
So that was a non-answer, but I don't know.
It helped, thank you. And was in any way Hawkins, you know, when somebody like that vanishes from the science, does he leave any gaps? Like you say, you need another Einstein. Are there any Hawkins gaps left?
I think I just want to connect to my phone because I'm losing. Sorry, I didn't hear that, Mick. Did you say, you know, we've lost someone like Hawking and?
No, I was just wondering, in the same way that you said we're waiting for another Einstein,
Yeah.
Is there any gap left where Hawkins was at?
Yeah, I think so. I mean, Hawking did a lot of amazing stuff, you know, that was not entirely this quantum gravity, but a lot of work around black holes and radiation that we should see from black holes. So, yeah, and there's lots of people working in that field. I have to say I'm not totally up to speed with all of what's happening, but I think there's space for some real creativity.
Vanessa, I was wondering about non-rotating black holes. Do they have a different history, a different evolution from rotating black holes?
I think so. I think that non-rotating black holes probably don't exist. I think that non-rotating black holes have only been considered because it's so much easier to solve Einstein's field equations when you don't have rotation. So the first solution, like the one that I showed you here, that was done by Carl Schwarzschild, was for non-rotating black holes. And that's just because it was a lot easier. So once you add rotation, those equations become far more complicated. And they have been solved. I mean, as you've heard from other questions in the audience. Mm-hmm. But I think in nature, I can't imagine, unless we, you know, at least in the context where I've described, we have either a massive star or potentially even a black hole at the center of the galaxy. I think all of those are probably rotating black holes.
Irrespective of their size. So you're going to find the same with stellar and with supermassive.
Yeah. So there's one theory that suggests, I think, very low mass black holes, these little primordial black holes. What if you just had sort of black holes bubbling up when the universe started? Or some people even thought you might see them, you know, when CERN had this Large Hadron Collider. So there was this kind of wonder if we'd see these very sort of low mass black holes. I mean, it's possible that those may be non-rotating, but at the moment, those are all still figments of imagination rather than even circumstantial evidence to show they exist.
Right, thank you very much.
Cool.
Has anyone else got any questions they'd like to ask Vanessa?
Derek,
I thought the rotation was set up due to the energy that was transferred when a mass is captured by a black hole. Is that correct?
Well, I think it could be because, as you say, I mean, basically some torque is added as material is captured and spirals in. But I think at least in some cases, they probably are formed in a rotating. They formed rotating. And angular momentum, you're right, angular momentum can be added certainly in the process. But it's strange because there's that weird theorem like about black holes. What is it called? Black holes have no hair. They have no real properties except for their mass, their rotation. And is there another one? It's charge or something, right?
Can I ask a quick question? You mentioned in the beginning that there's been a lot of new developments on fast radio bursts. Am I allowed to ask about that? Is there something
Yes, you can.
to say there?
Yeah, well, I think for a start, loads more radio bursts have been discovered since I gave you the talk, but also a few repeating radio bursts have been discovered. So these things have now generally been thought to be from much more distant sources, so outside of our own galaxy. Of course, there has to be an exception. So somebody has seen a series of radio bursts from a magnetar. And a magnetar is an incredibly highly magnetized neutron star. So again, it's the core of a massive star. So the outer layers have been blown off in a supernova explosion. The core remains as this very dense object, rapidly this magnetar has given rise to some of these fast radio bursts. So it's very tantalizing, actually. Oh, and something else that's interesting is, and I don't actually know how to explain this. You'll have to get Amanda Weltmer to give you a talk because it's really her field. But because those fast radio bursts have been detected way outside of our own galaxy, cosmologists are thinking of using them as potential distance measures in the universe. So I think that's something that Amanda would be great at talking about.
Intriguing. Thank you.
Thank you. Are there any other questions for Vanessa? Any other questions?
You said that black holes launch jets. So what are those exactly? Are they stars or what?
So these jets are actually just probably, so I think the short answer is we don't know. We see the jets because we see radio emission in these very narrow collimated, sort of collimated jets. And we think that radio emission can come from electrons that are spiraling in magnetic fields. So the electron goes round and round the magnetic field line like that, and then it's because it's decelerating, you end up with it giving rise to a radio photon to get rid of some energy. So we think it's probably from that. There are other ways that you can make the radio emissions. You can even make with much heavier particles like protons. But, you know, it's a really good question because nobody actually knows how these things are launched. You know, it's one of those things where we see these jets at all different scales, and we also see them when we've got disks of material around the central black holes or neutron stars. But how exactly does this disk of material launch a jet out of two different poles? You know, no one's really figured that out yet. So,
thank you.
But it's probably particles. We don't see the particles themselves. We just see the radiation from the particles.
Oh, all right. All right.
Cool.
Well, if there aren't any further questions, Vanessa, I'd love to thank you very much indeed for a fascinating and, as people have said, a superb presentation. Thank you very much indeed for your time and all the effort you've put into putting it together.
Yeah, thanks, Vanessa.
Thanks very much, Jenny and everyone else. I hope next time I see you in Hermanus.
That would be nice. Thank you very much and have a very good evening.
You too. Bye, everyone.
Bye.
Okay, I'm going to log off then. Thanks, everyone.
Thank you very much, Derek.
Okay,
Bye.
Bye.
bye.